Your brain can reconstruct a complete, high-resolution memory from a single sensory fragment, a familiar voice, or a partial silhouette. Computational models called Hopfield networks attempt to mimic this by retrieving full patterns from noisy data. But these classical systems have a hard limit. If you store more than 14 patterns for every 100 neurons, the memories interfere with each other and the data becomes a scrambled mess. Modern high-capacity networks solved this storage bottleneck, allowing us to pack thousands of memories into small grids. However, that capacity relies on a process known as synchronous updates. In a synchronous system, the computer calculates the state of every single neuron simultaneously at every time step. This requires intense, power-hungry parallel processing. Brute force calculation is standard for a cloud server, but it creates a total mismatch for the small, autonomous, low-power processors we are trying to build. This mismatch has led hardware engineers to neuromorphic chips, silicon designed to mimic the physical structure and energy efficiency of the human brain. These chips operate on event-driven or asynchronous updates. Instead of calculating everything at once, computation happens one neuron at a time, and only when a specific signal triggers it. The problem is that traditional high-capacity software often breaks down when forced to run sequentially. It gets trapped in loops or generates false memories. A recent paper explores a way to bridge this gap using Kernel Logistic Regression, or KLR, networks. The goal is to determine if KLR networks can maintain their massive storage capacity while updating one bit at a time, finally making high-capacity AI compatible with ultra-low-power silicon. To maximize storage, the researchers tuned the network's kernel locality, the gamma dial, to 0.1. This optimizes the system to isolate and protect thousands of memories simultaneously. This chart tracks recall accuracy against storage load. Across all tested network sizes, accuracy remains a perfectly flat line at 1.0. Even at a massive load ratio of 30, the network doesn't crash, demonstrating capacity orders of magnitude beyond classical models. When we look at the retrieval process starting from 20% noise, the results are identical. The blue solid line for parallel updates and the red dashed line for sequential updates overlap perfectly. The math indicates that switching to sequential, power-saving updates doesn't cost the network anything in terms of speed, capacity, or accuracy. We visualize memories as an energy landscape. Memories are deep valleys. Errors are high peaks. Older systems create jagged terrain, where sequential updates get stuck in false cracks. KLR networks instead carve large margin attractors, smooth, frictionless funnels where data reaches the absolute bottom. Because these slopes are engineered without obstacles, the order in which neurons update is irrelevant. The data will always slide directly down to the absolute bottom of the memory basin. This smooth geometry enables a level of error correction efficiency that has significant implications for physical hardware. This chart tracks the total number of events, or bit flips, required to fix a noisy memory. The red line, the actual cost, sits almost exactly on top of the black dash line, which represents the theoretical minimum number of errors. The network isn't guessing or bouncing around. It identifies exactly which bits are wrong and steps directly towards the target attractor. Consider the physical trade-off. To fix 10 errors in a 50-neuron network, a synchronous system would evaluate every neuron 3 separate times, requiring 150 total evaluations. The asynchronous KLR network performs exactly 10 targeted evaluations. It flips only the broken bits and immediately powers down. By shifting the heavy lifting to the mathematical optimization of the memory landscape, we remove the choice between massive AI capacity and ultra-low power consumption. This proves that event-driven computing is ready to support high-performance associative memory on the milliwatt power budgets required for decentralized